fundamental. Why do gravitational waves travel at the speed of light?
It sounds like just a fact,
Right?
right? But it's actually uh, deeply woven into the fabric of physics.
Exactly. And confirmed with, well, just staggering precision. So our mission today is to walk you through it, all the theories, the math.
The quantum ideas, and crucially, the experimental proof.
Right, to really unpack why this speed see is so fundamental. Have you ever wondered, what is a gravitational wave and why does its speed even matter that much?
It's a great question to start with.
Okay, so let's unpack this a bit. For, well, centuries, the picture was Newton's gravity, wasn't it? The sort of instantaneous action at a distance.
Like the Earth instantly knows the sun is there, no delay.
But then Einstein came along and, well, that picture just shattered.
It really did.
Yeah.
Because Einstein's special relativity, even before general relativity, established a universal speed limit. See the speed of light.
Nothing faster. No information, no cause and effect.
Exactly. So, instantaneous gravity. That just couldn't work. It would break causality. It created this huge conflict.
So understanding the medium, as you put it, space-time itself,
Yeah.
that became the key.
Absolutely. Resolving that clash between Newton and special relativity meant rethinking gravity entirely.
Okay, so if Newton was out, how did Einstein's big idea, general relativity, change the game regarding this speed limit?
Well, general relativity, unveiled back in 1915, wasn't just a tweak. It was a complete revolution in how we see gravity.
Right, it's not a force pulling things across space anymore.
No, it's the geometry of space-time itself. Gravity is the curvature of this four-dimensional continuum.
The classic analogy is the bowling ball on the rubber sheet, right? Creating a dip that other things roll into.
Precisely. It's the shape of space-time guiding motion. And John Wheeler had that wonderful saying.
Oh yeah, space-time tells matter how to move, matter tells space-time how to curve.
That's the one. And it's not just mass doing the telling. It's all forms of energy and momentum.
Light, pressure, everything.
Everything bundled into what physicists call the stress-energy tensor. That's the source of the curvature.
Okay, so if the distribution of that stuff matter and energy changes, say two black holes merge.
Then the curvature changes. But that change can't happen everywhere instantly. It has to ripple outwards.
Like tossing a pebble in a pond.
Exactly. And those ripples, those changes in curvature, have to obey the universal speed limit. They have to travel at c.
So that's the first big piece. Gravity as geometry inherently requires a finite propagation speed.
It's built in from the start.
So these ripples are the gravitational waves.
Right.
But what actually generates them? Is it just any old movement of mass?
No, not quite. It takes something specific, the asymmetric acceleration of mass.
Asymmetric, how does that compare to, say, light waves?
Well, light comes from changing electric dipoles. Think positive and negative charges oscillating. But gravity, well, it only has one charge, mass energy. And it's always positive.
So no simple back and forth like electric charges.
Right. There's no gravitational dipole radiation in the same way. Gravity needs something more complex, a changing quadrupole moment.
Quadrupole, like something changing shape.
Yeah.
From a sphere to an egg shape, maybe?
That's one way to think about it. Or, more practically in astrophysics, you need something like two massive objects orbiting each other rapidly, constantly changing the distribution of mass energy in a non-spherical way.
It's fascinating, isn't it, how the nature of the source dictates the type of wave.
Absolutely. Because mass energy is always positive, you need this more intricate dance to shake space-time effectively.
So the really energetic events are the key sources then. Binary neutron stars.
Binary black holes, yes. Asymmetric supernova explosions, too. Those are the powerhouses.
And when one of these waves passes by us, what does it actually do? You mentioned strain.
Yeah, strain is the term. Imagine a circle of free-floating objects. As the wave passes through, the circle will get squeezed in one direction while being stretched in the perpendicular direction, then squeezed the other way, back and forth.
It's literally stretching and squeezing space itself.
That's right. But the effect is unbelievably tiny.
How tiny are we talking?
The strain is typically less than 1 part in 10 to the power of 20.
Wow. So changing the distance between Earth and the Sun by less than an atom's width.
That's the scale, which tells you why detecting them was such an incredible challenge for so long, and why detectors like LIGO and Virgo had to be so unbelievably sensitive.
Okay, that lays out the concept beautifully. But let's get into the weeds a bit. How does the math itself, the actual equations of general relativity, lead to this speed?
Right, the core of GR is the Einstein field equations, the EFE. They're the mathematical heart.
The cosmic rulebook.
A good way to put it. They describe how space-time's geometry, The metric responds to the stress-energy tensor within it.
You mentioned they're complex. What's the main difficulty?
It's their nonlinearity, gravity. Well, it gravitates.
Meaning gravity itself has energy, which creates more gravity.
Exactly. It feeds back on itself, which makes the equations incredibly hard to solve exactly in most situations.
So how do physicists actually study waves using these equations?
They use a very important tool, the weak field approximation.
Okay, sounds like a way to simplify things.
It is. It's valid far away from very strong sources where space-time is almost flat, like Minkowski's spacetime from special relativity.
So you treat gravity as just tiny ripples on an otherwise flat background.
Precisely. You say the full space-time metric is the flat metric plus a small perturbation, a tiny wobble.
And that makes it more like electromagnetism.
Yes, it linearizes the equations, making them much easier to handle, very much analogous to Maxwell's equations for light.
Now, you also mentioned something called gauge invariance in GR. What's that about? Sounds technical.
It is a bit, but the concept is important. It's basically mathematical freedom. Think of map coordinates. You can use latitude, longitude, or UTM or something else.
Yeah.
The actual landscape doesn't change, just your description.
Okay.
Gauge invariance in GR means we have freedom in choosing our spacetime coordinates. This freedom can sometimes hide the physics or make the equations look messier than they need to be.
So physicists fix the gauge.
Exactly. They apply a specific mathematical condition, like the Lorentz gauge condition, which simplifies the equations and helps isolate the actual physical wave-like part of that perturbation. It's like choosing the best coordinate system to clearly see the ripple.
And here's the payoff, right? After applying the weak field approximation and fixing the gauge, what form do the Einstein field equations take?
This is where it gets really elegant. They boil down to the standard homogeneous wave equation. You see this equation everywhere in physics for things that propagate as waves.
The D'Alembert operator, the box symbol acting on the perturbation equals 0, box bar.
That's the one. And the crucial part is what that operator represents. It inherently contains the speed of propagation.
So the speed of light, c, isn't something you put into the equation at this stage?
No, it pops out of the equation. It's embedded within the structure of the D'Alembert operator itself, which comes directly from the underlying flat space-time metric. The math forces the waves to travel at c.
A mathematical inevitability. Wow.
It truly is.
That connection is powerful. And it leads us naturally to compare gravitational waves with, well, the most familiar wave traveling at sea light.
Absolutely. The comparison is really insightful. We know James Clerk Maxwell unified electricity and magnetism back in the 19th century.
And his equations predicted electromagnetic waves,
Ah,
light, traveling at a specific speed.
right. And if you write Maxwell's equations in the same four-dimensional space-time language physicists use for GR and apply a similar Lorentz gauge condition to the electromagnetic potential of mu,
Don't tell me.
you get the exact same mathematical form. A bunch is note the standard wave.
Yeah.
Bopal dollars.
Standard wave equation.
So mathematically, linearized gravity and electromagnetism look incredibly similar in this weak field limit.
Profoundly similar. They both yield this identical wave equation structure.
What did that imply, fundamentally?
It strongly suggests that c isn't just the speed of light. It's the fundamental propagation speed for any massless relativistic field disturbance in spacetime. It's baked into the geometry itself. Okay, so they share this fundamental speed, c, but goodness, they are so different in almost every other way.
Oh, completely different beasts. We touched on some differences already.
Yeah, the source. For one, gravity comes from the stress-energy tensor, this complicated rank 2 thing.
While electromagnetism comes from charges and currents, a simpler rank 1 vector source.
And the radiation type, gravity's quadrupole, EM's usually dipole.
Right. Gravity only has one type of charge, mass energy, always positive, always attractive in the classical sense. EM has positive and negative charges, attraction and repulsion, shielding.
And the strength, gravity is just incredibly weak compared to EM, right? Like 10 to the 36 times weaker at the particle level.
Astonishingly weak, yes. And even the quantum particles are different. The hypothetical graviton is spin 2, the photon is spin 1.
So a whole list of differences.
A huge list. But despite all that, in a vacuum, their waves propagate at the exact same speed c. That speed limit is imposed by space-time itself.
Fascinating. Okay, let's shift gears slightly and look at this from the quantum perspective. We know forces in the standard model have carrier particles, bosons?
Right. Photons for EM, W and Z for the weak force, gluons for the strong force.
And a classical field, like an electromagnetic wave, is essentially a macroscopic manifestation of huge numbers of these quantum particles.
Exactly. So if gravity fits this pattern, there should be a quantum particle for it too.
The graviton. Still hypothetical, but predicted.
Yes, we don't have a full quantum theory of gravity yet, but we can infer properties the graviton should have, if it exists, based on classical GR.
Like its spin. You mentioned spin 2. Why spin 2?
Because its source, the stress energy tensor, is a rank 2 tensor. The spin of the mediating particle is related to the rank of its source. A vector source, like EM's forecurrent, corresponds to a spin 1 particle, photon. A tensor source implies a spin 2 particle.
Okay, that makes sense. And what about its mass?
This is key. We observe that gravity acts over infinite distances. Its influence doesn't seem to drop off faster than inverse square, even on cosmic scales.
Unlike the weak force, which has a tiny range.
Exactly. And in quantum field theory, the range of a force is inversely related to the mass of its carrier particle. Infinite range implies zero mass.
So the graviton must be massless, just like the photon for the infinite range electromagnetic force.
That's the inference. Massive carriers like the W and Z bosons lead to short-range forces. And this directly connects mass to speed in the quantum realm via special relativity.
How so?
Special relativity is very clear about this.
Okay.
Any particle with non-zero rest mass must travel slower than c, always.
Okay.
And any particle with zero rest mass must travel at exactly c. It has no choice. Photons, for example.
So let's connect the dots. Infinite range for gravity implies
A massless graviton
and a massless particle must travel.
at exactly c.
So the quantum picture requires gravitons and therefore gravitational waves, which are made of them to travel at the speed of light.
Precisely. It's a completely independent line of reasoning, rooted in quantum mechanics and special relativity, that arrives at the very same conclusion as classical general relativity.
That consistency is just beautiful. It really strengthens the whole picture.
It's one of the things that gives physicists confidence they're on the right track, even without the full quantum gravity theory.
Okay, so we have theory, we have math, we have quantum arguments, all pointing to C. But for about a century, this was all still, on paper. Then came the breakthrough, the experimental proof.
August 17th, 2017. A date now etched in physics history.
GW 170817, the binary neutron-star merger.
That's the one. Detected by the LIGO and Virgo gravitational wave observatories.
And what made this one so special wasn't just seeing the gravitational waves, right?
Correct. The crucial thing was that neutron-star mergers were predicted to be multi-messenger events. They should produce not just gravitational waves, but also electromagnetic radiation, light, gamma rays, etc.
A cosmic explosion sending out signals in different forms.
Exactly. And GW 170817 delivered. It essentially set up a cosmic race.
A race over an incredible distance. Where did this happen?
In a galaxy called NGC 4993, about 140 million light years away.
140 million light years. That's the racetrack. So what happened?
Well, the LIGO Virgo network detected the gravitational wave signal, the chirp of the merging neutron stars, at 12.41.04.4 universal time.
Okay. And the light signal?
Just 1.74 seconds later. At 12.41.06.1 UTC, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst, GRB 17087EA, coming from the exact same patch of sky.
Wow. 1.74 seconds. After traveling for 140 million years.
Think about that journey. That's over 4 times 10 to the 15 seconds. A delay of less than 2 seconds over that time is, well, it's almost nothing.
It's an incredibly tight finish to the race.
And that tiny delay allowed physicists to put an unbelievably strict limit on any possible difference between the speed of gravity and the speed of light.
What was the result?
The analysis constrained the fractional difference,
Yeah.
Lenny COC, to be between -3 times 10 to the -15 and +7 times 10 to the -16.
Okay. Translate that. Minus 15 plus 16.
It means they are the same to within about 1 part in a quadrillion,
Mm-hmm.
1 part in 10 to the 15.
1 part in a quadrillion. That's just mind-boggling precision.
It obliterated previous, much looser constraints. This one observation improved our knowledge by about 14 orders of magnitude. It was astounding.
And they checked other things too, right? Like the arrival times at different detectors?
Yes, that gave a secondary, less precise, but still important check, confirming the speed was consistent with c as the waves passed through Earth, ruling out certain medium-dependent effects.
It was just an absolute slam dunk for Einstein then.
An unambiguous verdict. It wasn't just confirmation. It was a powerful testament to the predictive power of general relativity, a century after it was proposed.
Okay, let's play devil's advocate for a moment. What if? What if GW 170817 had shown a significant difference? What if Weyler's was not equal to C?
Ah, the counterfactual. Well, that would have been earth-shattering for physics. It would immediately imply that the graviton has mass, molars in mil/pen.
And that would mean general relativity itself is wrong, or at least incomplete.
Fundamentally modified, yes. The wave equation wouldn't be the simple one we discussed. It would be a massive wave equation, like the Klein-Gordon equation.
What would the consequences be?
Two big ones immediately come to mind. First, gravitational waves would exhibit dispersion. Their speed would depend on their frequency or wavelength, like light through a prism. Lower frequency waves might travel slightly slower, for instance.
Okay, and the second?
The gravitational force itself would change character over very large distances. It wouldn't follow a strict inverse square law forever. It would decay faster, more like a Yukawa potential. Gravity's reach wouldn't be truly infinite.
Now, people have explored these massive gravity theories before, haven't they? Weren't there problems?
Oh yes, serious problems historically. Early theories in the 70s ran into something called the VDVZ discontinuity. Van Dam, Veltman, and Zakharov.
Catchy name. What was the issue?
Basically, even the tiniest hypothetical graviton mass led to predictions that just didn't match observations, like predicting the wrong amount of light bending by the sun only 3/4 of the GR value. It didn't smoothly connect back to Einstein's theory as the mass went to zero.
Not good.
And later, a more deadly problem emerged in many theories: the Boulware Desert Ghost.
A ghost. Sounds spooky.
It's a theoretical pathology. It means the theory predicts particles with negative kinetic energy, which leads to instabilities. The vacuum itself could decay explosively. Very bad news for a fundamental theory.
So, lots of problems. But didn't interest in massive gravity make a comeback recently? Because of dark energy?
Exactly. The mystery of the universe's accelerated expansion, usually attributed to dark energy, prompted some physicists to reconsider modifying gravity on cosmological scales. Maybe a tiny graviton mass could mimic dark energy.
A way to avoid needing this mysterious energy component filling most of the universe.
That was the hope. And new, more sophisticated theories like DRGT gravity were developed, claiming to be ghost-free and potentially viable alternatives.
So how did GW17-817 impact those modern theories?
It delivered a swift, powerful blow.
Because the speed was so close to c.
Precisely. That tiny $10–15 constraint on the speed difference translates directly into an incredibly tight upper limit on the graviton's mass.
How small are we talking?
The limit is around millidollar less than or equal to $7.77 times 1023 electron volts over c squared. That is fantastically tiny. For perspective, its Compton wavelength would be over 1.6 light years.
So functionally zero for almost all intents and purposes.
Practically indistinguishable from zero, and this limit was devastating for many of those alternative gravity models proposed to explain cosmic acceleration.
Why?
Because many of them required a graviton mass large enough that it would have produced a speed difference much, much larger than what was observed in GW17-017.
So the observation just ruled them out.
It cleanly sliced through that theoretical landscape, yes. It showed that if the graviton has mass, it must be so incredibly tiny that it's unlikely to be the explanation for cosmic acceleration. It dramatically narrowed the viable options, reinforcing standard GR plus dark energy.
What an incredible story, bringing together so many threads. So let's just recap the main points here. DEM isn't just one fact.
No, it's this amazing convergence.
We have the theoretical necessity from gravity being space-time curvature.
Right, changes have to propagate.
The mathematical inevitability from the Einstein field equations themselves.
The wave equation pops right out with C.
The structural analogy with electromagnetism, another massless field.
Both obeying the same fundamental wave dynamics.
The quantum mechanical requirement, linking infinite range to a massless particle traveling at c.
An independent line of reasoning.
And finally, boom, the experimental verdict from GW17-817.
Confirmed to 1 part in a quadrillion. Unambiguous. You know, it's more than just finding the speed of a wave. It really speaks to the fundamental nature of spacetime, the unity of physical laws. It shores up general relativity tremendously and gives us this fantastic tool, these waves, to explore the universe in a completely new way.
Absolutely. So the next time you hear about LEGO or Virgo detecting merging black holes or neutron stars, just take a moment to appreciate the incredible journey those ripples took, traveling across millions or billions of light years at precisely the speed of light, carrying secrets about the most extreme events in the cosmos. It makes you wonder, what other fundamental constants or principles have such a rich, interconnected story just waiting for us to uncover as theory and observation keep pushing the frontiers?